Hello and welcome everyone. Today we have an exciting online session where we will be exploring the fascinating world of circles and angles. In this session, we will focus on the relationships between different angles within circles. We will talk about three special angles called the inscribed angle, the central angle, and the angle of tangency. And we will also explore the concept of the cyclic quadrilateral, this special shape that fits perfectly inside a circle. And to make things even more fun and interactive, I encourage you to pause the video and try out the challenges I will be presenting. Take your time to solve them and then check your solutions against mine. So let's get started on this exciting journey into the world of circles and angles. Let's get started. Remember these words: pass, perpendicular, bisect. Pass through the center of the circle and perpendicular to any chord, and bisect is the chord. The straight line passing through the center of the circle and perpendicular to any chord will bisect this chord. So here we have a straight line, and this straight line is passing through the center of the circle M and is drawn perpendicular to the chord AB. So this straight line bisects AB. So you'll find AC here in this case is equal to BC. Here in the second figure, we have a straight line passing through the center of the circle and bisects this chord, is drawn here passing through the center of the circle and bisect this chord. So this straight line will be perpendicular to this chord, is perpendicular to the chord AB. So here, in this case, you will find MC, the straight line MC, is perpendicular to AB. Here in this shape here, we have a circle and we have a chord. And this line is drawn perpendicular from the midpoint, perpendicular to this chord from the midpoint. So this straight line will pass through the center of the circle. So this straight line will pass through the center of the circle. So just remember these words: pass through the center of the circle, perpendicular to any chord, bisects this chord. The tangent is perpendicular to the radius from the point of tangency. So here we have a tangent and we have radius. The tangent is perpendicular to the radius from the point of tangency. So this angle is right angle. And here we have a diameter and we have BC. I don't know what is BC, but if this angle is 90, ABC is 90. So if we have a straight line and this straight line is perpendicular to the diameter from one of the two end points, so this straight line will be a tangent. So this straight line is a tangent if this angle is 90. And the two tangents drawn from the two end points of a diameter are parallel. So this tangent here and this tangent are parallel. To identify the circle, we must know the center and the radius. To draw the circle, okay, to draw a specific circle, we need to know the center of the circle and its radius length. How many circles passing through a specific point? We can draw actually an infinite number of circles passing through a point. So here we have a point A, and I'm asking about how many circles passing through this point. We can draw an infinite number of circles. We can draw an infinite number of circles passing through this point. What if we have 2 points? How many circles passing through these 2 points. Just to draw some of these circles, join up AB, and then draw an axis of symmetry. What is the axis of symmetry of AB, and how can you draw it? Hold your compasses and draw an arc here at the top, an arc down, up and down. By the same opening, draw an arc here, an arc here. Then join up them. That's the axis of symmetry of AB. So the axis of symmetry is the straight line perpendicular from the midpoint of AB. Now all circles passing through A and B lie on this straight line, lie on this axis of symmetry. So put your metal tip here on any point and draw a circle passing through A and B. So we have an infinite number of circles passing through AB, like I'm drawing now. So here we have a circle, and that's the second circle, and we can draw another one. Here it's the third circle. So we can draw actually an infinite number of circles passing through the 2 points A and B. Just the first step, draw an axis of symmetry of AB. Then put the metal tip at any point, then open the compasses, open your compass at A or B, and then you can draw a circle. What if we have a specific line segment AB, okay, and I want to draw a circle, and the radius of this circle is greater than half AB. So how can we draw this circle? The first step, draw AB by using the ruler, then draw an axis of symmetry of AB. So let's say AB equals 6 centimeters. And I want to draw a circle of radius length greater than half AB, let's say 5 centimeters. So here we can draw 2 circles. Just open your compasses at 5 centimeters, put the metal tip here and draw an arc here. Put the metal tip here, this distance here is 5. Then draw a circle. You can draw one circle here, up, it centers above AB, and we can draw another circle, its radius below AB. That's it. So here we can draw 2 circles. If the radius length, so let's assume that AB is 6 centimeters, and I want to draw a circle, its radius is 3 centimeters. So here we can draw only one circle because we are going to draw AB 6 centimeters, okay? And the radius length is 3 centimeters. You will draw an axis of symmetry. Then you will open your metal, your compasses at 3 centimeters. So in this case, you will find the center of the circle lies here in this point. So we can draw only one circle. And if the radius length is less than half AB, so here it's AB 6. I'm assuming a number here, AB is 6. And I want to draw a circle of radius length, let's say 2 centimeters. So here, whatever you draw a circle of radius length 2 centimeters, you will find the circle less than AB, the length AB. So we couldn't draw a circle here. So in this case, the number of circles can be drawn 0 circles. So we couldn't draw circles here. And if the radius is equal to half AB, so we can draw only one circle. If the radius greater than half AB, we can draw 2 circles. How many circles can be drawn passing through 3 collinear points? 3 collinear points means they lie on one straight line. Actually, we couldn't draw a circle passing through 3 collinear points. So here we can draw 0 circles. But if we have 3 non-collinear points, like these points A, B, and C, we can draw only one circle. If we join the A, B, and C, we will get a triangle, and the number of circles passing through these points, it's only one circle. So we can draw one circle. The circle which pass through the vertices of a triangle is called the circumcircle of the triangle. It's called the circumcircle. Once again, the circle which pass through the vertices of a triangle is called the circumcircle of the triangle. The perpendicular bisectors of the sides, of a triangle intersect at a point which is the center of the circumcircle. So here, I want to identify the center of this circle. Draw an axis of symmetry, the perpendicular bisector. So here, the perpendicular bisector from the midpoint, I'm going to draw a line. Okay, do you with me? This line is perpendicular bisector. How can we draw a perpendicular bisector? By using the compasses. So imagine that this is the line segment. I'm going to draw a perpendicular bisector. So put the metal tip here of the compass, draw an arc up and down, and here draw arc up and down, and join up them. That's the perpendicular bisector. So here, just put the metal tip here at the point A and the metal tip here at the point B by the same opening. Draw an arc here up and down, and for B, draw an arc here up and down by the same opening. Join up them, you will get a perpendicular bisector, and do the same another perpendicular bisector for the line segment AC. So you'll get here a perpendicular bisector, and here we can draw a perpendicular bisector by using the compasses. And this point here is the center of the circumcircle. By using the compasses, put the metal tip here at this point, then draw a circle passing through these points. So in the acute angled triangle, you will find the center of the circumcircle lies inside the triangle, What if we have right-angled triangle? Draw an axis of symmetry for this side, and axis of symmetry for this side, and axis of symmetry for this side. You will find that the center of the circle lies in the midpoint of the hypotenuse. Okay? Put the metal tip here of the compasses, draw a circle passing through these points here. So the center of the circumcircle in this case lies in this point here. This point is the center here is the midpoint of the hypotenuse. When it comes to the obtuse angled triangle, follow the same steps. Draw an axis of symmetry of this side and axis of symmetry from this side. You will find the two axes of symmetry and an axis of symmetry for this side. You will find the three axes of symmetry. The axis of symmetry is the perpendicular bisector of this line segment. This point here is the center of the circle. Put the metal tip here of the compasses, draw a circle passing through these points. What I want to say here in this case, that the center of the circumcircle lies outside the circle. If we have equal chords, that leads to get equal distances. So here in this circle, we have the chord AB equals the chord CD. So the distance from the center to this chord MX is equal to the distance from the center to CD. So just remember, equal chords leads to get equal distances. Equal chords, equal distances. So here AB is the chord AB, and here CD is a chord, and they are equal. AB equals CD. So the distance must be perpendicular. So MX here in this case is equal to MY. And also if we have equal chords, then that leads to get equal arcs. So here we have a chord AB is equal to the chord CD. So that leads to get the arc AB is equal to the arc CD. Once again, if AB equals CD, the code equal to the code, that leads to get the measure of AB arc is equal to the measure of CD arc. That's it. And if we have parallel codes, so the arcs included between them are equal in measure. So here AB is parallel to CD. We have two parallel codes. AB is parallel to CD. Then the arc AC, measure of the arc AC, is equal to measure of the arc BD. They are equal in measure. And here we have a code parallel to a tangent. So the two arcs included between them, the arc AE is equal to the arc BE. This arc here is equal to this arc here. The measure of the arc AB, you know, the measure of the whole circle is 360. The measure of the whole circle is 360. And the length of the whole circle, the length means circumference. The circumference of the circle equals 2 pi r. So here it's the measure of the circle, and here it's the length of the circle, the circumference of the circle. What if I want to find the length of an arc, like the arc AB? There is a kind of relation between the central angle and the measure of the opposite arc. The central angle is equal to the measure of the opposite arc. So let's say this angle is 70 degrees. So the measure of this arc is it will be 70. They are equal in measure. What if I want to find the length of AB? You know, the length here of AB is a part of the circumference. Okay, so here we will find the measure of AB, divided by 360, because the whole circle is 360, multiplied by the circumference, and the circumference is given as 2 pi r. So we will find the measure of the arc AB divided by 360 multiplied by the circumference 2 pi r. That's it. Types of angle inside the circle. This angle here is central angle, and the central angle, its vertex at the center of the circle, and the two sides of this angle are two radii in the circle. So we have here MB is radius and MA is radius, and the center of the circle is M. And the measure of this angle, the central angle, is equal to the measure of the opposite arc. So the central angle is equal to the measure of opposite arc AB. So the central angle is equal to the measure of the arc. And this angle here is an inscribed angle. And the vertex of the inscribed angle lies on the circle. And the two sides of this angle are two chords in the circle. And the relation between the inscribed angle and the opposite arc, the inscribed angle is equal to the half of the opposite arc. So if this arc, let's say 110, so the measure of this angle is 55. The inscribed angle is half the measure of the opposite arc. And here the central angle, if this arc is 110, so the central angle will be 110. And this angle is angle of tangency. And the vertex of the angle of tangency, like the inscribed angle, lies on the circle. And the two sides, one of them is a chord in the circle. So here AB is a chord and AC is a tangent. And this angle here, angle BAC, is called angle of tangency. And the angle of tangency is equal to half the measure of the opposite arc. So it will be half the arc AB. Half the arc. So if this arc is 110, so this angle is going to be 55, half the opposite arc. If we look at this angle, we will find the inscribed angle here and the central angle, both of them are subtended by the same arc. So the measure of the inscribed angle is half the measure of the central angle. Okay. So if the central angle is 120, so the inscribed angle is equal to 60 directly, because the inscribed angle and the central angle are subtended by the same arc. Here we have a central angle and the angle of tangency. What is the relation between them directly? Because they are subtended by the same arc. Okay. So here, the angle of tangency is half the measure of the central angle. So if the central angle is 130, so the angle of tangency will be 65 because they have the same arc. Here we have a tangent and a chord, so this angle is angle of tangency, and this angle is an inscribed angle, and they have the same arc. So here if this angle is 65, so this angle directly will be 65 because they have the same arc. If two chords intersect at a point inside the circle, then the measure of the included angle here equals half the sum of the two measures of the two opposite arcs. So here, simply, this angle here is the intersecting angle between the two chords here. So angle X here equals half the sum. Half the sum of what? Half the sum of the two arcs included between them. So if this arc, let's say 70, and this arc is 60, so this angle here, X, is half the sum of 70 plus 60. So it will be half of 130 equals 65 degrees. Here we have two rays, and the two rays intersected outside the circle. So the intersected angle here, X, equals half the difference. So X here equals half the difference. Half the difference between what? Between the major and the minor arc. So X here, let's take values. Let's write here 120 and angle here, let's say 50. So what is X here in this case? X is half the difference. Half the difference, 120 minus 50. So it's half the difference. 120 minus 50 is going to be 70. So half 70 equals 35 degrees. So once again, if the angle inside the circle, by the way, it's not an inscribed angle or central angle. This angle is an intersected angle between two chords equals a half sum. And if the angle was outside the circle, so the size of this angle would be half the difference between the two arcs. Okay. The inscribed angle drawn in the semicircle is right. This angle here is an inscribed angle. And this is a diameter. The inscribed angle drawn in the semicircle directly is right angle. So if you found an inscribed angle and you found a diameter, the two end points of the two sides of this angle, we join them, you will get a diameter. So here the opposite side to this angle is a diameter. So this angle directly is right. The inscribed angle, which is drawn in a semicircle, is right angle. If we have inscribed angles subtended by the same arc or drawn on the same arc. So here we have angle 1, angle 2, angle 3, and they are all equal in measure. Do you know why? Because they are drawn on the same arc directly. So here, if we have two equal arcs, so the two inscribed angles drawn on arcs which are equal in size, so they are equal in measure. That's it. What is the cyclic quadrilateral? The cyclic quadrilateral is a quadrilateral figure whose four vertices belong to one circle. So here we have A on the circle, B is on the circle, and C lies on the circle, and D lies on the circle. So this shape, this quadrilateral is cyclic. So here the point M, you will find the distance here for the length of MA is the same as MB, is the same as MD, is the same as MC. So what are the properties of the cyclic quadrilateral? All vertices lie at equal distances from the center of the circle, from a point inside this quadrilateral. And the two opposite angles are supplementary. So angle A and angle C are supplementary, add up to 180. So each two opposite angles, the two opposite angles are supplementary. Two opposite angles equals 180. And the exterior angle, if we join the side here, BC on the extension of BC, you will get an exterior angle. The exterior angle here is equal to opposite interior, is equal to angle A here. They are the same. So each two opposite angles are supplementary. The exterior angle equals opposite interior. And if I said to you that this shape here is a cyclic without drawing a circle, so you will find, like I'm drawn now, this angle here labeled 1 and this angle labeled 2. They know they are drawn on the same base. So they are equal in measure. So the size of angle 1 equals the size of angle 2. Do you know why? Because they are drawn on the same base or drawn on the same side of the cyclic quadrilateral. So angle 1 equals 2 and angle 3 and angle 4, they are equal. Do you know why? Because they are drawn on BD. So each two angles drawn on the same base are equal in size. The quadrilateral is a cyclic if one of the following conditions is satisfied. Number 1, if there is a point in the plane of the figure such that this point is equidistant from its vertices. Number 2, if there are two equal angles are drawn on one of its sides, Number 3, if there are two opposite supplementary angles. Number 4, if there is an exterior angle at any of its vertices equal to the measure of the measure, equals to the measure of the interior angle, equals to the measure of the interior angle at the opposite vertex. If the two circles are touching externally, so Mn here equals R1 plus R2. So Mn here equals the sum, R1 plus R2. And if the two circles are touching internally, so Mn, the line of center, equals the difference between them equals R1 minus R2. And if the two circles are two distant circles, so you will find Mn equals a value greater than the sum. So Mn here in this case is greater than R1 plus R2. So it's an interval from the sum greater than the sum till positive infinity. So it's R1 plus R2 and infinity. And if the two circles are two intersecting circles, you will find here Mn is greater than the difference between the two circles and less than the sum of the two radii, sorry. So it's greater than the difference and less than the sum. So N here, the line of centers is greater than R1 minus R2 and less than R1 plus R2. So it's an interval. It will be greater than R1 minus R2 and an interval it's R1 plus R2. That's it. So if the two circles are two touching externally, Mn equals the sum. So let's write here, they are touching externally. And if the two circles are touching internally, they are touching internally. So Mn equals the difference. And if the two circles are two intersecting circles, so Mn, the line of centers, is greater than the difference and less than the sum. And if the two circles are two distant circles, so Mn is greater than the sum. If the two circles are one side the other, so Mn is less than the difference between the two radii. Mn here is less than R1 minus R2. So Mn is greater than 0 and less than the difference. So Mn belongs to the interval 0 opened and R1 minus R2. And if the two circles are two concentric circles, so Mn equals 0. So let's summarize them. If the two circles are two concentric circles, so Mn, the line of centers, equals 0. I'm talking about the length. If they are touching internally, so Mn equals the difference between the two radii. And if they are touching externally, equal the sum of the two radii. And if one of them inside the other, so Mn is an interval. It's greater than 0 and less than the difference. So interval from 0 opened to the difference between the two radii. And if the two circles are two intersecting circles, so Mn is greater than the difference and less than the sum. So it's an interval, the difference and the sum. And if the two circles are two distant circles, so Mn is greater than the sum. So it will be equal to R1 plus R2 and positive infinity. How many tangents can be drawn from a point on the circle? It's only one tangent. We can draw only one tangent from a point on a circle. From the two endpoints of a diameter, we can draw two tangents, and the two tangents are parallel. So we can draw two parallel tangents. And from a chord inside the circle, we can draw two tangent segments, and the two tangent segments will meet at a point outside the circle. So here A and B, we can draw a tangent here to the circle, and from B we can draw a tangent. And as you see here, the two tangents intersect at a point. And this AC is a tangent segment. AC is a tangent segment. And BC also is a tangent segment. And you will find that AC equals BC. And also from a point outside the circle, if we have a circle like this circle, and from a point outside the circle, like this point, how many tangents can be drawn? Actually, you can draw two tangents. Here it's a tangent, and here it's a tangent. If we join this point A and B, you will get a code, and this code is called code of tangency. Code of tangency. And as I said, AC, the tangent segment AC, is equal to the tangent segment BC. The straight line passing through the center of the circle and the intersection point of two tangents bisects the angle between these two tangents, bisects the angle between these two tangents here, and also bisects the angle between the two radii passing through the 2 points of tangency. So this angle here is equal to this angle. So as you see here, they are two congruent triangles, and the angle colored in blue is the same as angle colored in blue, and the angle colored in black is the same as this one colored in black, and the angle colored in red is the same as this one, and the angle labeled crossing it the same as this angle. This angle is inscribed circle. And the inscribed circle of any triangle, if I want to find the center of this circle, we can get the center of this circle from the point of intersection of the bisectors of its interior angles. Bisector, so here the center of the circle, we can get it, the center of the inscribed circle, we can get it from angle bisectors of its interior angles. So if we're going to bisect this angle and bisect this angle and bisect this angle, they will meet at a point, this point at the center of the circle. So the center of the circle is the point of intersection of the bisectors of its interior angles. How many common tangents of two distant circles? We can draw 1, 2, there are 2 tangents, and 3 here, and 4 here. So we have 4 common tangents. If the 2 circles are 2 intersecting circles, so you will get 2 tangents, 2 common tangents. If the 2 circles are touching externally, you will get 3 common tangents, 1, 2, 3. And if the 2 circles are touching internally, you will get only 1 tangent, 1 common tangent. And if the 2 circles are one inside the other or 2 concentric circles, you will get no common tangents. I hope you enjoyed this session. See you in the coming episode. Goodbye.